Alright, since we've been talking about area, we're going to talk about Riemann sums, and specifically with equal widths. So let f be some sort of function, continuous and non-negative on the interval between a and b. And then a Riemann sum estimates distances. It could estimate the area, the total cost, and so on, depending on the situation, by the sums of the area, the rectangles of n subintervals called partitions. So what we're doing is we're creating a bunch. We have an area with a curve. We are creating rectangles to estimate the area underneath the curve from a starting point A going to an ending point B. That's what we're doing. And so to find the Riemann sum, if you're of equal, or n is the different widths of the rectangle are equal, then essentially all the areas, area of rectangle number 1 plus area of rectangle number 2 plus area of rectangle number 3 and so forth, all the way to the last rectangle. So n is the number of rectangles with equal widths. And so each rectangle's area is, is height times width. So the width of each rectangle, we're going to call it delta x. That's the change of x. How far apart is the width of each rectangle? And so if you want to think about it, delta x is going to be b minus a over n. So what I mean by that is if you want to find the width, you're going to take the whole entire interval, subtract it so you know the distance between them, and then you want to divide it by how many rectangles you have, and that's going to give you your width. There are going to be times where they go ahead and give you delta x, and then you don't need to worry about using your whole entire interval, dividing it by the number of partitions. If f is an analytical equation, not a table or a graph, then you're going to just go ahead and set up a table where x's can count by your width, your delta x, and the f of x is going to be the height at that particular x value. If the problem situation determines which height to use. So there's going to be times where the problem's going to say, I want you to find the left height. So then we're going to talk about, we call it LRAM, but essentially it's an approximation with a rectangle having to be on the left-hand corner. And then the right height would be the height on the right corner. The lowest height, sometimes they'll call this inscribed rectangle, so that means that your rectangles are always going to be beneath the curve. The greatest height means the rectangles are always going to be above the curve. Those are circumscribed rectangles. And sometimes we take the average, we'll average things, and we'll find the middle rectangle. That we call this the midpoint. And there's going to be times where you're going to be given a table. If you've been given a table, then just find the change in x, how far apart x is, and then just by looking at that change in x values. If they're consistent, then that change in x values is your delta x. So we're going to look at a couple different problems. We're going to be practicing a little bit more in class, doing lots of activities. Alright, number 1, set up an approximation of the area of the function y equals the square root of the quantity 1 minus x squared using LRAM, that means the left-hand Riemann sum, with 5 rectangles of equal width over the interval from 0 to 1. So let's first find the width. And so again, the width means it's going to be width is delta x. And so what we're talking about is what is the change of x? Similar to slope, if you want to think about the change of y over change in x, that's kind of what we're thinking about, how far apart x. That's going to be equal to, so let's find out the width. We're having 5 rectangles. If our total distance for the rectangles goes from 0 to 1, so we're doing 1 minus 0. So that's my total distance, and I want to figure out what the distance of each part. I have 5 rectangles, that's my n. Then I want to figure out the width per rectangle is going to be 1/5, or if you want to think about it, it's 0.2. So now let's go ahead and set up our chart. And so I'm going to have x, and on the bottom I'll have f of x, aka y. And so x starts at 0, and if my change of x each time is 0.2, so I'm going to go up, and next one's going to be 0.2, and then my next one up is going to be 0.2 plus 0.2 is 0.4, Then my next one's going to be 0.6, finally 0.8, and then and our last one is 1. And so we want to find what is the y for each of these values. Alright, so to find my f of x, I'm going to plug in my x coordinate, my x's, and so if I plug in 0, 1 minus 0 is going to be 1. I'm going to go ahead and cheat and use a calculator. 0.2 is going to be 0.979. 0.4 is 0.916. 0.6 is 0.8. 0.8 is 0.6. And 1 is 0. And so we're talking about a left approximation. We're talking about values to the left. And so if you want to look at it, in terms of our chart, we're going to pick values that are on the left. So we're not going to include this guy over here. We're not, because we're talking about an LRAM deals with a left sum. And so we're talking about values to the left. So we're going to multiply my height times my width and add it to each of these rectangles. So height times width, height times width. So my width is 0.2, so my height's going to be 1 times 0.2 plus 0.979 times 0.2 plus 0.916 times 0.2 plus 0.8 times 0.2 plus 0.6 times 0.2. So my area is approximately, so my height, so we'll do height or width times height. So my width is 0.2 times my height, which is 1, plus my width, which is again 0.2, times my height, which is 0.979, plus dot, 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 dot. And so you notice I'm multiplying by 0.2 each time. So what I could do instead is I can multiply by 0.2 at the end. I'll factor it out. Well, that means I'm just going to be adding 1 plus 0.979 plus 0.916 plus 0.8 plus 0.6. And then at the end, multiply by 0.2. And when I do that, I will get 0.859. And so that is the approximate area underneath the curve. And so let me give you a quick picture of what I'm talking about here. If I was going to graph these points, it's going to look something, my graph is going to look something like this. So each of these, if I break up from 0 to 1, I break up to widths of 1, 2, 3, 4, and here's my 5th one. And I create rectangles. I'm going to create a rectangle that has the height of the left-hand corner of my rectangle. So this one's going to have a height here. This one's going to have a height, goes a little bit above it right there. And then the next one. And then the next one. Sorry about my one rectangle is the wrong height. This guy right here. Sorry about that. But the idea of it is you're using the left-hand corner of your rectangle. Those are these. That's the left-hand corner, left-hand corner, left-hand corner, left-hand corner, left-hand corner. In reverse, the right-hand corner, we would start over on this guy with the 0. But since it says in LRAM, we're going to start with the left-hand corner. So number 2, set up an estimate of the area between the curve g of x and the x-axis using the lower Riemann sum with 4 subintervals from going from -2 to 2. So I'm starting at -2 here, and I'm going to +2. So I'm going to create rectangles. And I'm just going to, it's just an estimate of the area underneath this curve. And they want using the lower Riemann sum, so that means we're talking about inscribed rectangles. So if it's lower, that means I'm going to create rectangles that are below the curve. Okay, and so sometimes it might be a right Riemann sum, sometimes it might be a left Riemann sum. I know, so here I kind of gave you an idea what your inside rectangles look like, so I can't go above the curve, I'm going underneath the curve. If you notice, the corner of my rectangle on the left-hand side create a left Riemann sum, an LRAM. However, on the right-hand side, I'm using the right-hand corner. And so these create a right Riemann sum. And so we're just going to approximate my delta my delta x, if you notice, we're talking about 4 subintervals, so that means I'm going to have 4 rectangles. You can see that my delta x is going to be equal to 1. And so what I can do is my area is approximately 1 times the sum of each of these heights. So we'll call this, I don't know, 1.2 plus, I don't know, 2.8. This guy right here, plus, let's say 1.5, plus, let's say maybe 0.5. And so that's approximately, let's see, I guess about 6. And so that's approximately the area underneath the curve.